Hello, and this is where we review everything we learned about similarity. Of course, by way of review, we just work a lot of standardized test sample problems. If you want to review anything else, well, unlike instructors, I'm on file. You can replay absolutely any video and review anything you want. So, how do we know that ABC is similar? Remember, that means similar there, to EDC. Yeah, it's pretty easy. Remember, vertical angles are congruent, and they tell us that these two angles are congruent. Well, we've got our angle-angle theorem, which says that if the two angles are congruent, we have at least similar triangles. We could have a similarity ratio of 1, meaning that they're congruent, but they have to at least be similar. Find the value of n. Well, that's not too bad. We just have to, of course, recognize that in similar triangles, the ratios will hold all the way through. All we have to do is figure out which are the corresponding sides. The side opposite these two congruent angles, so side n corresponds to this side here, which is of length 10, so 10 over n. And all we have to do is find two other sides which correspond. And opposite this angle is 6. These two angles correspond. Or these two angles are congruent. These two angles are congruent. And as we know from way back a long time ago, that means these two angles also have to be congruent. Opposite this congruent angle is, or this part of the congruent pair, you could say, is 4, and opposite this is 6. So we have 10 over n is equal to 4 over 6, or 4n equals 60, n equals 15. Now, the perimeter of ABC is 22. Well, the perimeters are going to be in exactly the same ratios as the sides. Or we can apply, you could say we can apply our similarity factor to the perimeter, and it'll still work. For instance, AABC, that's the small one here, has a perimeter of 22. So, even if we didn't know what n was, we could figure this out because we still have this. And in this case, the perimeter would be our small perimeter, which is 22, over the perimeter we don't know, equals 4 over 6, or we could write this as 2/3. And that gives us that 2p equals 66, and p equals 33. Or about 1.5 times this, which makes perfect sense, because if this is 2/3, the small one is 2/3 of the big one is 3/2 of the small one. So our answer makes sense, and we're done. And in this one, they tell us a whole bunch of stuff. AB, that's this here, is parallel to HC, that's this piece here, and GD, that's this piece across here. So we got these three parallel lines, segments. We have AG is congruent to BD. Here's AG, and here's BD. So these two have the same length. First question, find BD. Well, they just told us that AG and BD are congruent. What's AG? 30 plus 11 is 41. So BD here must be 41. What about BC? Well, we know that parallel lines break these segments up in equal proportions. The segment is HG over HA has to be the same as DC over CB. And we also figured out in a previous section that if the separate segments both have the same ratio, we could take CD over BC, CD over BD, which is the short one over the whole, and that has to be the same ratio as HG over the whole. The problem is, this whole thing here is 41, just like this one. Well, if our ratio of CD over 41 is going to be the same as 11 over 41, CD is going to have to be 11. Or if I wrote it out, this is 41, right? So this is 41, the whole thing. Let's see if I can. Which means that CD over 41 equals HG over 41. But HG is 11. Well, the easiest way to produce this equality is to make CD 11 also. Boom, now they're both equal. And that's what I did. And exactly the same thing will work here. So BC, that has to be 30. Now, for part B, I want us to take a look at this support here, MP. And it's fixed at the point P, N, and M. Well, being fixed like this, we know it's in the same plane as these two. For instance, this one here, this isn't. This is well, it's kind of like the third leg of a tripod. This is not in the same plane as all this stuff here. This straight line here, this is. So we can use everything we know about transversals and parallel lines and all that good stuff, depending on what questions they ask. What are they asking here? It's attached. NP equals 10 inches. I guess I can just write it in here. That's 10 inches. Find MP. That's the entire length. Well, once again, remember, parallel lines break things up into equal ratios. So 10 over the whole, that would be MP, is equal to 11 over the whole, which is 11 over 41. Or 11 times MP equals 410. Now, if we set up the ratio, remember it has to be the same. Each of these is broken up by the parallel lines in exactly the same proportions. So 10 over MP, that's the whole, is exactly the same as 11 over BC. That whole would be 41. Now when we lay that out, we get 410 equals 11 times MP, or MP equals 37. Now that means that this length here is 27. That's MN equals 27. They didn't ask you for this length. They asked for the whole. But in your book, it may list the answer here as 27. That's wrong. It's 37. And if you're not convinced, well, consider this length here is 41. If this entire bar here, from here to here, was only 27 inches, well, that makes it Now what do we got? 10 plus 4, 14 inches. These two bars will be 14 inches longer than this, and that just doesn't make any sense. As you can see, the angle here would not be enough to make this piece that much shorter than the distance in this direction. In other words, if this was 27 and this was 41, these would have to angle way out here like this for that to work. That way, if these were 41, they'd stop around here somewhere, and then this would be 27. As it stands, that's not a very big angle here, which means that these sides are only going to be slightly longer than this centerpiece. And if this centerpiece was 27, that'd be way too long. On top of which, algebra doesn't lie. Check the algebra, and you will see that 27 cannot be the right answer for MP. It is the right answer for MN. I think this was probably just a misprint. I think I've pointed out before. The authors of this book are fairly brilliant, and they wouldn't make this mistake, but the printer or somebody could have easily accidentally written MP instead of MN, and so they actually solved it correctly. This part got written wrong. So MP is 37, MN is 27. And down here they're asking you a question. They want to know if polygons AM, NH, if polygon AM, NH is similar to AM, PG. Well, there's one quick, easy way that you can say no to this. AM, this side here, is shared by both polygons. And that makes it, in this case at least, the corresponding part of both polygons. So the ratio of this section on one polygon to this section on the other polygon is 1. It's just AM over AM. On the other hand, if we take the ratio of, say, this side to this whole side, that would be 30 over 41. Well, whatever that is, it definitely isn't 1. And to be similar, all the ratios have to be the same all the way. The ratios have to be the same all the way through. And the simple way to point out that they aren't is to just see that AM over AM is 1, and none of the other ratios are going to turn out to be 1, because these things are definitely not congruent, and that's what has to happen for the similarity ratio to be 1 all the way across, or all the way through. So the answer is no. When you cut a triangle with a line parallel to the opposite side, then you end up with two similar triangles. But you can't just do that with any old polygon. It doesn't hold. Here's one. They're asking us about two rugs. And I think the first question is, are they similar? The first one is 24 by 16, and the other one is 36 by 24. Well, let's check. We got 24 over 16, and that is equal to, less than, greater than 36 over 24. Well, let's see here. If we divide both of these by 8, I think we get 3 over 2. Divide each of these by 12, and we get 3 over 2. Well, okay. They are the same ratio. The rugs are similar. Now, the perimeter and area of each rug, and then find the ratios of the perimeters. Well, heck, I think we already know the ratios are going to be 2 to 3. But if they want us to do it the long way, I guess we can do that too. For a rectangle, perimeters are very easy. is remember you've got a rectangle with a width here and a length here. So the perimeter is just W plus L plus L, which would be 2W plus 2L. That's all we have to do for perimeters. So it's going to be pretty easy to work this out. For the smaller rug, we have 2 times 24. Plus 2 times 36. So if we perform those calculations with the small rug, we get 2 times 24 plus 2 times 36, which is 120. Now, the big rug, we could use what we already know and multiply this by 3/2. That's going to be 180. Or, we can do it the other way. 2 times 36 plus 2 times 24. Well, I just made a dopey mistake. 24 and 36 are the dimensions of the large rug, not the small one. If I want the perimeter of the small rug, I need to multiply 120 by 2/3. Yeah, this is 40 times 2, and that's 80. Or, we could pick 2 times 24, which is 48, and 2 times 16, which is 32, and that equals 80. We could have gotten at the second perimeter either way. If you're going to use the similarity ratio, that's fine, but you're going to have one of the other perimeters to do that. Once you've got one perimeter, you can use your similarity ratio to find the other. So, now I went ahead and wrote in what we did here, or I should say, what we found, so as to erase what was to the right and give us more room to work with here. So far we found that they are similar. The similarity ratio is 2/3. We found the perimeter of the small rug, the perimeter of the large rug. The ratio of the perimeters is 2/3, exactly what we expected. But now, what about the areas? Well, let's find out. Although the ratio of the small one to the large one for the areas is going to be the square of this. But let's find out how that works. We'll do it, I guess we'll do it in concrete terms, and then we'll show why it's always true. The area is, of course, for the small one, just 16 times 24. You remember that, just length times width. It's, in a sense, even easier than the perimeter. So the area of our small rectangle is 384. 16 times 24. The large rectangle, 24 times 36. Well, these are actually rugs, not rectangles, pardon me. But mathematically, they're still rectangles. And the large one is 864. So what's the ratio? 0.444. Well, in fractions, that number is very related to this. Let's do this in general terms. Remember, our ratio is 2/3, right? So if we call the large one A inches long and B inches wide, then the small one, well, we'll start with that one. The area of the large rug would just be A times B. What about the small one? Well, we know our ratio now, so for the small one we have 2/3 A. That's our new length, and 2/3 B is the length of the smaller one. And what does that work out to? Well, that's 2/3 squared times AB. What is 4/9 in a decimal representation? 4. It just goes on forever. So, the perimeter has the same ratio as the sides of the similar polygons. However, the area, well, it has a ratio equal to the square of the similarity ratio. So, we'll say the area ratio is 2/3 squared. And in general, whatever the scale factor is, the area is going to be k squared. If the image is A, if the original is A and the image of B is kx and kb, scale factor is k, then the area is going to be changed by k squared. It'll either get smaller, as it did in this case, as we went from the large rug to the small one. And remember, a number less than 1, when you square it, becomes smaller than itself. Like 1/2 squared becomes 1/4. 1/3 squared is 1/9. When you square numbers between 0 and 1, they get smaller, not bigger. Which means that with two similar polygons, the areas get smaller faster than the perimeters. The perimeter is 2/3 of the original, but the area is 4/9, which is less than 2/3. Remember, 2/3 is 0.666. 4/9 is 0.444. Okay, now we get to the making of the rug. 250 feet of yarn to make 1 square foot of rug. Okay, this doesn't sound too tough. All we have to do is figure out how many square feet there are in each rug, multiply that by the 250, and that'll tell us how much yarn was used. Now let's see here, 250 feet of wool for each square foot, and we have our rugs in inches. So we're going to have to do some conversions here, aren't we? Which do you want to convert? We have this in inches. So if we convert this to inches, we won't have to do any more conversions. We'll just do everything in inches from there on. I guess we could do that. We'll just have some big numbers. For instance, 1 square foot, well, that's 12 times 12 inches, or 144 inches. That's 1 square foot. 250 feet. Well, how many inches is that? Well, that's just 12 times 250. So with a little bit of calculating, we can figure out that 250 feet of yarn is 3,000 inches. And 1 square foot of yarn is 144 square inches. So, we're using 3,000 inches of yarn per 144 square inches of rug. If we were to multiply this by the number of square inches in the rug, boom, we'd have the number of inches of yarn that was used. So, first thing I need to do is rewrite this in a way that we have room to write everything down. Up here I wrote the areas that we computed earlier. Area of the small rug, area of the large rug. how many inches of yarn for each rug? Well, let's start with the small rug. 384 square inches of rug. Why am I writing all this out? So that I can see that I am in fact canceling things out here. I've got square inches of rug down here in the denominator, square inches of rug up here in the numerator. They'll cancel, and my answer will be in inches of yarn, which is what I want. So now all I have to do is figure out what this great big number is. 384 times 3,000 divided by 144. And I'm going to ask my calculator. And my calculator says that 3,000 times 384 divided by 144 is 8,000, and that's inches of yarn. That's the small one. What about the big one? Well, I could take this, multiply it by 864, or I could take the answer I've already got and multiply by 3/2. That seems easier to me. Suppose I, in other words, scratch that. We can't do that, can we? Because we've got areas here. And the area is not going to be 3/2. It's going to be 3/2 squared. What's 3/2 squared? 9/4. If I multiply this by 9/4, I should get exactly the same thing I'll get when I multiply this by 864. So if I do it this way, I get 18,000. And if I do it the long way, I still get 18,000. Why? Well, essentially, if I replace this 384 with 9/4 of 384, and then pull the 9/4 out, I have this equation right here. If you get what I mean. In other words, in order to compute the large area, I could have done it this way. Instead of 864 in here, I could have written 9/4 times 384. When I do that, I can pull the 9/4 out and put it out here in front, and then I've got 3,000 over 144 times 384. That's exactly what I had here, which we know is 8,000. So this and this part without the 9/4 would give us the 8,000. And then 9/4 of that will give us the 18,000. So you could do it either way. You could recognize that the ratios of the areas is going to be the square of the ratios of the sides, and just use that number right there. Or you could do it the long way, which would be putting 864 in here and performing this calculation again. Either one will give you the right answer. It's up to you what you prefer. So the answer is, it took 8,000 inches of yarn to make the small rug, and 18,000 inches to make the large one. And at the very end here in part D, the owner is charging 1.5 times as much for the large rug as the small rug. And you can see the sense of that because the similarity ratio from the small to the large is 3/2, which is 1.5. But that's the similarity ratio for the sides. It would really make more sense to price it according to the areas, not the lengths. If you were selling string, for instance, or rope, then if one rope was 1.5 times as long as the other rope, you might price it as 1.5 times as much. That would make sense. But when you're talking about something rectangular, where one of the sides is 1.5 times as much, what does that mean? That means the area, as we've already figured out, is 3/2, 1.5 of that, or 3/2 squared. And that's 9/4. In other words, the ratio of the areas is 9/4. And we already worked that out, in fact. 864 over 364 is 9/4. Or if you want to put it in the same decimal terms as this, well, that's 2.25, right? So he's, from a buyer's point of view, you're getting a much better deal if you buy the large rug, because you're getting a lot more material per dollar than you're getting with the small rug. And that's because areas grow much larger than lengths. Assuming that your lengths are the measurements of some polygon, areas normally grow as the square of the lengths. In other words, when you double the sides of a polygon, say a rectangle, make them each twice as long, the area is now 4 times as large. And that's pretty much always true for areas. You can expect areas to grow or shrink as the square or square root of the linear dimensions. But that's all kind of general. For what we're doing right now, you just have to remember that for similarity transformations or similar polygons, your similarity factor gets squared when you're worrying about how the ratio of one area to another. For the perimeters, this stays the same. But for areas, don't forget that your scale factor gets squared when you compare one area to another area. So I don't think here it is right here. 2.25 would actually be or 9/4 would be the right answer. Okay, this one, well, first off, I moved the diagram to the bottom. It's not really on the right anymore. Hope that doesn't confuse you. OQ passes through the origin. Okay, how do we know that OPS is similar to OQR? In other words, how do we know that this small triangle is similar to this big one? Well, we already know that if we cut a triangle with a line parallel to one of the sides, we will automatically produce another similar triangle. So all we need to figure out is, are these two lines parallel? Well, RQ is perpendicular to the x-axis here. If PS was perpendicular to the x-axis, we'd be done. Is it? Well, let's see here. This has an x-coordinate of 5. This has an x-coordinate of 5. That means this is a vertical line, and that means it is in fact perpendicular to the x-axis. All we have to do is spot that the x-coordinates are exactly the same. They made it kind of easy for us, so we know that they're similar. And if we didn't like that way of doing it, well, that's good enough. We'll just stop right there. Now, find the coordinates of the point Q. Well, this is perpendicular, so we know that it must have the same x-coordinate. So there we go. On the other hand, they're similar. This one has a length of 3, right? It goes from 0 to a y-coordinate of 3. So the ratio of this side to this side must be the same as the ratio of this side to the whole. That would be this side on the larger triangle. In other words, this part corresponds to this on the large triangle, and this side here corresponds to this side on the larger triangle. Well, this is 5 and this is 9. In other words, it's 5 to here and it's 9 from the origin to this endpoint. So we can write that 5 over 9 equals 3 over, let's call it x. That's this length we're trying to find right here. And that gives us that 27 equals 5x. You know, it's confusing having x coordinates and then using an x here. That was kind of a mistake. I shouldn't have done that. Since it's actually the y coordinate we're looking for, why don't I just use variables that show that very directly. 5 over 9 equals 3 over y. So y must be 27 over, 27 over 5, or 5.4, I think. Either one would be good. So this length here, we'll say it's 5.4, which means that our y coordinate here must be 5.4. And that's because we started down here at the x-axis where our y coordinate was 0. If our y coordinates weren't 0 along here, we'd have more arithmetic to do, but it would still be doable. So coordinates for q are 9, 5.4, or 27 over 5. And for the last one, that's going to be fairly easy. If we think of the x-coordinate as a, write the y-coordinate, well, gee whiz, that's kind of like the equation of a line, isn't it? And what's the rise over the run here, which will give us our slope? 3 over 5, and that's the slope for this line here. So y equals 3/5 times a plus the y-intercept, which is 0. So the y-coordinate given any point A, the y-coordinate is going to be 3/5 a. I think it's obvious here that the equation for the line is y equals 3/5 x, but they asked for the expression in terms of a, so we have to put an a in here instead of an x. But keep in mind that a and x are actually the same thing because they told us so right here. Here we're given two triangles. We're told that they're similar. And I went ahead and sketched them in here. It's frequently easier if you have a picture to work from. And then I want to know which one of these isn't necessarily true. Now let's take a look. PQ, that's this section here, to QR is the same as ST over TU. You know why this would be true? Our similarity theorems don't say too much about the ratio of, they talk about the ratio of the two similar triangles, not the ratio of a triangle within itself. This is the side of this triangle, and this is the side of the same triangle. But remember our theorem says we can switch the means and write the, if we write this, we could switch these two means and end up with PQ over ST equals QR over TU. Now PQ over ST, that would be this length over this corresponding length, and QR, or pardon me, yes, QR over TU, well, that's this side over this side. And so that would be true. So this is just a rewrite of PQ over ST equals QR over TU. then we swap the means and we end up with this expression. So this would necessarily be true, even though right off the bat it doesn't look like you would know this from the fact that they're similar. You just have to recognize that this is a true statement where the means have been interchanged. What about this? PQ, that's this side again, over SU. That doesn't look too good. It's the same as PR, that's this one, over TU. Well, I think they're mixing up the sides. You see, SQ, or pardon me, PQ over ST, and PR over SU, that would make sense. This one looks a little strange to me. But let's check the other ones just in case. PR over SU, PR over SU, that's just what I was talking about. And QR over TU. Okay, here we have the ratios of the corresponding sides are the same, and that's what this statement says. So this is true. PQ over PR, PQ, PR, ST, SU. Well, let's try swapping the means again and see what happens. We get PQ over ST and PR over SU. So with A and D, these are true statements derived from a very simple true statement about the ratios, and then we swap the means. Or going in reverse, we swap the means and then we end up with a true statement based on the fact that the two triangles are similar. And this one is just a statement that's always true for similar triangles. But this one here, I don't see any way we can definitely say that this side, the ratio of this side to this side, is going to be the same as the ratio of this side to this side, because they're not corresponding sides. And there's also no way we can swap the means. We could swap the means here. We got PQ over PR, but now we're just back inside the same triangle. And remember, similarity doesn't say anything about the ratios of one side to the other side of the same triangle. It has to be one side of a triangle to another side of a similar triangle. So B is the one that we couldn't necessarily be sure of. And here's one that's very easy. The two cities are 2 3/4 inches apart on the map, but every inch is 80 miles on the map. This is a very, very simple demonstration of how to use scales on a map. All you have to do is take the number of inches that you have and multiply it by 80. And if we do that, we get, well, 2 3/4 is 11 over 4, right? Times 80 miles, we get 220 miles, and that's this one here. If you want to keep dimensions into it, it's very similar to going back and forth between feet and inches or feet and yards. It's as if we have a whole new type of conversion where 1 inch equals 80 miles. So if we put units into this here, what we should write is 11.4 inches. We got 11 over 4 inches, 80 miles per inch. And the inches cancel. We get 11 over 4 times 80 miles. So the actual distance, 220 miles. Now you can keep your dimensions in when you're doing these map calculations also, just to make sure you've got it all right. Just like you do when you're converting other units. Just think of a map as having, each map has its own distinct, unique unit conversion. In this case, it's 1 inch equals 80 miles. This one, they just want you to find the scale factor. Now, they're telling you that it's a dilation. So if we find one scale factor, it's the same for every side. For instance, this point V here, the image is R. Well, this is the 0.10, and this is the 0.30. So to get from, we'll say, the red triangle to the blue triangle, we had to multiply by 3. It's the same thing here. This is -2, and this, 4, 6. This is -6. So 3, that is to say a scale factor of 3, takes us from the red to the blue. However, they asked us how to go from the blue to the red. Just the inverse of that. 1/3. See? Real easy. Just find one of them, and they're going to be the same for all. The slowest and hardest way to work this problem would be to compute this length, and then compute this length. Use your distance formula, and then use your distance formula here, and you would get the same answer, but it would take you a lot longer. Well, this one here looks a little screwy, doesn't it? I mean, if you take a hard look at it. First off, by now you should recognize that we've got two lines crossing each other, and they're cut off at opposite ends with parallel lines. That means these two triangles are similar. And we showed that by pointing out that the vertical pair here is congruent, and that these two angles make opposite interior angles, and they're congruent. By the angle-angle theorem, these are both similar. But by now you shouldn't even have to go through that. You should just automatically spot we've got two intersecting lines cut by two parallel lines. We have automatically produced two similar triangles. We got a problem here, though. Usually one of these is known. So we've got a ratio made up of 3 numbers, well, 4 numbers, one of which is x, which is unknown. Well, this is going to be kind of strange, but we'll see what happens. These are the corresponding parts, by the way. This angle corresponds to this angle, so opposite sides means this side corresponds to this side. So we could write x over 9 equals what? 4 over x. Well, this isn't so bad. If we had x's in the denominator, we'd probably have a problem. But we can do this one. This implies that we cross multiply and we get that x squared equals 36. So x equals 6. Obviously, x could be -6 to satisfy this equation, but negative lengths don't make any sense, at least not in this class. So the answer would be 6. Well, let's see here. In this one, they're letting us know that PQM is similar to NMR. And NR is 12. Well, we know that NR is 12. They told us that. And PM, is that right? Yeah, PM is the corresponding side to NR. So if we knew the similarity factor, the similarity ratio, we could find PM real easy. But they didn't give us any other numbers. Jeepers, what do we do? Well, down here they tell us that these two sides, or segments, pardon me, these two segments are congruent. Well, this segment is just MR. That means this segment here, without any numbers, we don't know what it is, but we do know that this segment is two of these. They're both congruent, so MQ, we can just write it this way. MQ equals 2 times MR, or MQ over MR equals 2. So, turns out our similarity factor is 2. So, this is 24. All we had to do was recognize that since they told you that these two are congruent, this is exactly half of the whole. So, our similarity factor is either 1/2 or 2, depending on which direction you're going. And here's one. It's pretty easy if we remember. Well, not necessarily remember. First we have to notice that these two angles are congruent, and that makes this an angle bisector. And remember, where the bisector cuts the opposite side, it breaks it up into two segments that are in the same ratios as the adjoining sides. Now the ratios of the adjoining sides are 12 to 20, right? But we don't have this length here. We have the whole thing. But that's okay, because we can say that the ratio of, say, this to the whole will be the same as the ratio of this to the whole. In other words, the sum of these two. So instead of this, we can write 12 over 32, and that equals HE over 10. So, if we work that out, we get that HE equals 3.75. Well, let's see here. Would that make sense? That means GH would be 6.25, right? So let's try 3.75 over 6.25, and then 12 to 20. Well, if you work it out, you'll get that this equals 0.6. And you'll also get that this equals 0.6. So they're equal, and 3.75 is the right answer. Now, the problem here is, I went ahead and drew an isosceles triangle. We have an acute isosceles triangle, and this looks like an acute angle to me. The measures of two of the angles are on the ratio of 4 to 1. Well, remember, in an isosceles triangle, these two angles are congruent. So the 4 to 1 has to be this to this, or this to this. So I guess I can just label these like ABC and start referring to the angles the same as their vertex. So angle B let's set the measure of angle B equal to x. It'll make the equations go a lot easier. Now, they're in the ratio of 4 to 1. So if this is as measure x, and all we know is that one angle, either this angle is 4 times this, or this angle is 4 times this. I'm not sure if there's a way to know ahead of time which it is. If there is, I sure didn't spot it, because I assumed that this would be the larger angle and wrote that 4 alpha equals x. That's the 4 to 1. It definitely can't be this angle and this angle because they're equal. So if we go through all that, we also know that 2 alpha, that's the base angle here, so alpha plus x, that's 2 alpha plus x, equals 180. Well, we could use that to get an expression for alpha and put it back in here. When we do that, we get that our angle here, x, is equal to 120. That doesn't seem right. You know why it doesn't seem right? Because they tell us right here that it's an acute isosceles triangle. Well, with an angle of 120, it's not acute. So I've got the wrong answer. What did we do wrong here? Well, there are two choices. We could have had that x is 4 alpha, or we could have alpha is 4x. So let's try it the other way. Don't get dizzy. Let's write 4x equals alpha. This is the smaller angle, and this is the larger one. Then we have essentially the same equations to set up. 2 alpha plus x equals 180. The relationship between alpha and x doesn't change because of this. But now we have an equation. When we make our substitution, 4x equals alpha, we got an expression for alpha. We can write 4x equals 90 minus x over 2. We add x over 2, that's 1/2 x to each side, and get 4.5 x equals 90. Well, that leads to x equals 20. So this is a really small angle here. This is 20 degrees. What's left over? Well, they have to add up to 180. We've got 160 degrees left over, and we have to distribute them across two angles, which means 80 apiece, right? And I believe they asked, yes, they asked for the base angles. So your base angles are 80. Here's a 50-50 chance of guessing right. Well, I blew it. I hope you do better on your test. This is the wrong guess. 4 alpha equals x, that won't work. It's the other one. 4x equals alpha. That will work. Well, this one is it's pretty easy. Probably the first thing I would do if I saw a scale like this was convert it to 1 inch to how many feet. And remember, we can multiply through. In a ratio like this, we have 1/4 inch to 100 feet. If we multiply through by 4, we get 1 inch to 400 feet. And the question was, how far will the gym be from the art studio on your map if the gym is 400 feet? Well, jeepers, we just created a scale, 1 inch to 400 feet, which tells you the answer immediately. It's 1 inch. What about the second part? 1/2 inch equals 100 feet. Now, will the distance be greater than or less than? Well, the closer you get to the real distance, the larger your map is going to be. Unless, of course, you've made a map which has a scale that's even larger than the real thing. For instance, you have a map that covers, let's say, it's a detailed view of 1 acre of land, and your map takes up 4 acres. Well, that's a pretty crazy scale. The whole point of a map normally is to have something smaller than the original that you can look at more easily. A 4-acre map of a 1-acre area would not be easier at all. So assuming you're working with maps that are actually smaller than the real thing, the closer you get to a 1-to-1 scale, the bigger your map is going to be, and the farther apart things are. Now, 1/4 inch to 100 feet, 1/2 inch to 100 feet isn't a lot closer to 1-to-1, but it is closer, because 1 inch is bigger than 1/4. So, the distance, of course, will be greater, and we can easily compute what that will be. Let's put this on a scale of 1 inch to however many feet, and we'll get 1 inch to 200 feet. So 400, well, 400 feet is going to translate into 2 inches, isn't it? And 2 is definitely greater than 1. So it does get greater as your scale gets closer and closer to 1-to-1. Although chances are it will never get to 1-to-1. If it was 1-to-1, you might as well just, well, 1-to-1 would be way too big. That would be a hard map to fold and unfold. Okay, here's a problem that definitely makes use of proportions. I'm not sure I drew this accurately, but they say that the length is double the width. And let's see here, ABCD, that's the small one. The area of that is 32. I'm just going to write A sub S for small, and that's 32. Well, what is the area? Let's say this is, the width is X, and this is, length is Y, but wait a minute. We know that the length is double the width, so if this is X, we can just write 2X in here. Aha, well now we got something, because the length times the width is the area, and we know the area. I don't see, did they even ask for, okay, they asked for the length, width, and area of a different one. But we're still going to have to find this one, because, well, why? Because it's the only one we can find. We don't have any dimensions for this one over here. We don't know anything about this, except that it's similar to this one. So we better get some dimensions for this first, then we can figure out what's going on with the other one. So what we have here is 2x times x, or 2x squared equals 32. X squared equals 16, or, of course, x equals 4. So this is 4, and this is 8. So far, so good. Now they tell us what the ratio is. It's 3-to-1. So our work's almost done for us. I mean, if you can figure out what 3 times 4 is, and I'm sure you can, that's 12. 3 times 8, well, that's 24. And the new area, we can multiply 12 times 24, or it's a 3-to-1. And remember, areas move as the square of the similarity ratio. So this area will be 3 squared times this area. In other words, this side is 3 times this side. It's because our similarity ratio is 3. But its areas, as we compare the areas, they're going to be related according to the square of the similarity ratio, which is 9. So what I'm getting at here is 12 times 24, or 9 times 32, should work equally well. They should both give us the same number. Will they? Well, let's take a look here. Without even doing much arithmetic, we can probably prove that they're the same. 9 times 32. And instead of a calculator, just for fun, I factored them. Makes it easy to see that they're the same thing. 9 times 32 is 3 times 3 times 2 times 4 times 4. I could have broken it down to 2 times 2 times 2 times 2. On and on. I just stopped at 4 here, because when I do this, I can just rearrange these factors into 3 times 4 here, 3 times 4, and then 3 times 2 times 4. This is 12, this is 6 times 4, and that's 24. So 9 times 32, or 12 times 24. Give you the same answer. So the width was 12, the length was 24, and the area was 9 times 32, or 12 times 24. I forget what that works out to be, like 288 or something. Maybe I should have written the actual answer. And yes, 288 is the new area. And, well, that's about it. Remember, the next chapter in this series is trigonometry. In your class, the next chapter might be quadrilaterals, and the one following that will be trigonometry. In this series, the next one is trigonometry, followed by quadrilaterals. If you're doing it the other way, just skip ahead to quadrilaterals and then come back to trigonometry. Well, that's it for now.